Okay, so welcome everyone. I'm Mark. I'm a senior ML engineer at Kaiko, and first of all, I will introduce you a bit to Kaiko, and then I will go into my talk. So, we are a Dutch Swiss scale-up, founded in 2021. So we're not super old yet. We're an international team of about 60 employees, and we focus on building foundation models for oncology, so for cancer and curing cancer. Furthermore, we have a strategic partnership with the Dutch Cancer Institute, and we're also having our office in the hospital. So today I'm going to talk about leveraging Ray in our model development cycle to iterate multimodal oncology foundation models in the clinic. So first, I'll introduce you to these models and our clinical assistant. Then I actually take you through how we use Ray in this model development cycle. And finally, I'll go over some of the challenges we encountered or are still facing. But let's start with medical data. The journey of a cancer patient is, it's basically built around a wide variety of multimodal data, ranging from the text in their electronic health record to MRIs and CT scans from the radiology department, but also WSIs, for where the pathologist basically looks under the microscope through their cells. And all of these different data silos often resonate to a specific specialism in the hospital. For example, a radiologist, as said, looked at MRIs, a pathologist looks at WSIs, and so on. However, to actually diagnose a patient or come up with a treatment plan, you have to combine these modalities and together figure out what's going on and what is the best choice to make. So at Kaiko, we're on a mission to provide assistance in the clinic by enabling oncological foundation models. We work on a variety of models, both single modal and multimodal, that can help various medical experts in their daily work. Eventually, we work towards assisting these medical experts in actually curing patients. Now, to actually make this work, we introduce our multimodal assistant. It's named Kaiko Insight, and it provides an interface to the insights that are coming from the foundation models to, cure patients. So, to start, let's have a look at what Kaiko Insight actually does. Yes. So when you open the tool, it will load the data and infer with the models to gain insights on the specific patient that we're looking at. So here we see a patient, we see some personal data, but we also see some imaging results, some sample information, and this is a summary page, but actually today I want to focus on the pathologist view, which is the view that a pathologist would open to do their work. So here you see a whole slide image, which is an image taken under a microscope that shows, cells or a tissue that has cells in it, on which a pathologist can determine whether tumor is apparent and specific subtypes of that. And, normally a pathologist uses a zoom, either under a microscope or in their computer, to look in different stages towards the cellular level of these images to determine features of the patient. Now we enabled AI predictions on top. This helps the pathologist to, for example, see whether the model thinks there's tumor area apparent, but also what type of tissue we look at, whether there's metastasis, and also showing some confidences to actually know whether to use these. And let's now focus on our multimodal assistance. So here we have a chat, which you all know, that's the type of AI we use daily. And this chat has the picture, the context of the patient, and of course, a really broad range of medical knowledge. Now we can ask a question, such as whether the model thinks there's vascular invasion in these sections. And given that the model has access to the image, the patient data, but also all the medical knowledge, it can not only answer the question, but also provide assistance on next steps to take. Now, in this example, you saw a vision language model that is trained to understand both the visual context of a pathological image and the medical context of a patient and the medical experience of the doctor. It had this combined knowledge is normally used by a pathologist to actually diagnose a patient. And that's exactly what this model now can assist you with. So now you have some ideas of the assistant that we've been building. Let's take a look what's behind it and basically how it works technically. So behind all of those features in our assistant, we have multimodal foundation models or single modal foundation models. And many of those downstream tasks are driven by these models, which are heavy, need resources, need compute, need to be managed properly. And therefore, we leverage Ray and Kubernetes to make this setup efficient and scale well. So now let's dive into how we use Ray in our model development cycle. So here you see the cycle I meant. So first of all, we train a model. We then serve it to our clinical assistant. And then we validate it in the clinic to gain insights. We train the model using Ray Train, where we leverage PyTorch Lightning in AKS to utilize GPUs in an optimal manner without the engineers having to deal too much with the infrastructure. For serving, we leverage Ray Serve, and we actually serve all our models through a single application where the application builder is not that aware of the model served. It just requests an output from the model they need. And then finally, the validation we do with our medical ambassadors at the clinic. So we actually have our setup going and look with a pathologist or a radiologist into the different results to figure out whether we're doing the right thing. So now I'll first dive a bit into why it's difficult to deploy these models in production. So first of all, we have to ensure stable infrastructure and a proper security setup. The data in our system should remain private, as it includes many sensitive data of patients. And we have to comply with the local regulations, which in our case in the EU are rather strict. And furthermore, we need to make sure that the output of the model doesn't actually harm the patient or, well, any of the choices the doctor makes. Furthermore, we also need to make sure that our development cycle is consistent, efficient, and as much as possible automated so that our engineers can do their job. Next off is model management. We need to make sure that in this cycle, the right models are used at the right time. The versions need to align, and the models need to be kept up to date with the latest relevant versions. Furthermore, we need to make sure that the performance is staying as expected and is not drifting off in production. Next to that, we also need to make sure that in the different environments that we are using our models, both the data and the model versioning is similar, and that engineers can actually sort of expect that everything works as they expect it to work. And next to this, we as, well, basically platform building team, building a stack, but we're collaborating with a multidisciplinary set of teams where people both train models and also test them with the medical experts. This means that we have, on the one hand, engineers that are very in-depth, have a broad knowledge about the tool set and know what they want. But we also have people that just need a model to work and to get quick insights in the clinic. So on the one hand, we need to make sure our setup is customizable and the engineers are not complaining too much that they're restricted. But on the other hand, we also need to make sure that the less technically involved engineers can do their work quickly and are not running into issues in the clinic. To make sure the wheel isn't reinvented, we also want to make sure that models are discoverable and that features can be reused so that our engineers are not doing double work. But this talks about general cases that every company deals with. Let's now also go a bit into our setup in the clinic and why that's even more difficult. So first of all, these data restrictions. As I said, our data is rather sensitive, and therefore with the current hospitals we work, they don't want the data to leave their tenant. This brings the problem that we have to work with their on-premise systems and bring our models and compute to their site. Furthermore, data access is strictly managed, so it is on even a user level managed who can see what data from which patient. And that also means that for our engineers, it's very strictly managed which team can train data and therefore which models can expect which data. Second of all, we need to integrate with their systems, not only their on-premise infrastructure, but also the internal systems and the data models they use. This means that for every other client, you need a new transformation layer to make sure that our assistant can work with the different data silos in their hospital, and that we actually have a good understanding and alignment on what the data models actually mean. Next to this, we run it on their infrastructure, so we have to deal with their resources. Budgets are not as loose as in, for example, our own site or, well, many of the big companies that we've seen in the last days. So we have to be very strict with running GPUs, and serving models often have to scale down to 0 so that we don't use them too much. And then finally, let's talk a little bit about certification. As you might know, in the medical setup, there is a lot more restrictions in terms of what you can do with a model in production. This is regulated by the MDR in the EU or the FDA in the US. And this means that once your model actually influences choices that have affected a patient, you first have to get certified. For us, this means that in our development cycle, we also try to find how we can phrase our model and our assistant to not influence the patient's outcomes yet, so that we can quickly iterate without having to get certifications on everything we do. So now let's have a look at our training setup. So when we designed this setup, we kept 3 design principles in mind. First of all, reproducibility, so that we can audit any run we do, and we can also reproduce anything that has been run. Second of all, traceability. As I said, we need to manage the data access. So we want insight in who accessed which data, but also what data was used to train which model. And finally, to make sure that with all this strictness, our engineers are not annoyed too much, we want to keep in mind the path of least resistance. This, to satisfy our engineers, but also to overcome unnecessary blockers. So this is an overview of our training setup, and it might be difficult to look from this slide. I will dive in some of the details in the next slides. But one thing I want you to remember is that in our production setup, we have a single Ray cluster for a single team. This way we can manage the data access per team, and we can also manage the cluster access on a user level. So let's have a first look at the audit trail. So to make sure that we can actually reproduce what is happening and trace what has been going on, we audit every run we do. And this audit includes, for example, which user run this job, but also what data was accessed, and finally, which runtime environment was used to actually make this work. Then the data access. As mentioned, for every cluster, we have a managed identity. That is then saying that this cluster can use this managed identity to access data in our storage. On a dataset level, we now have access rules which define that, for example, a certain managed identity can read certain dataset or even write certain dataset. And in this way, we can very specifically track which cluster can access which dataset. And now coming to actually easing the lives of our engineers, we have introduced K-Ray. This is a tool that basically wraps the Ray CLI tool to make sure that an engineer that wants to access a cluster can actually access it. For this, we leverage the Ray job submit hook to first sign into Entra ID, make sure this user has access to the cluster, and when it has access, we authorize it and we forward the job. And if the user is not allowed to see the cluster, we actually prevent it and, well, stop the user from doing this. Another step we took to ease the life of our engineers is an environment resolver. So at Kaiko, we work with a monorepo, which has a lot of external and internal dependencies. So when an engineer wants to run a job, actually figuring out what are the dependencies and what are the local dependencies is quite a pain. Furthermore, we use PantsBuild to manage all this work in the monorepo. And on top of this, we have a runtime environment resolver that basically, given user wants to run certain scripts, we figure out what are the dependencies, what is the optimal environment, and forward this to the cluster so that every run has an optimal environment and different users can run very different jobs on the same cluster. Then finally, a short note on our development setup. Here, to actually test different things out and make sure that engineers can also test new things on Ray, we allow every engineer to host their own cluster using Helm and just basically spin up a new cluster to test certain things. However, this setup only has access to development or public data, so to avoid actually engineers just doing random stuff with our production patient data. So now that we've trained a model and are interested in the clinical performance, let's deploy it in our Serve application. Whereas training happened on our own tenant, in our own private environment, the models are served on the hospital's tenant, which actually includes some additional difficulties. So let's go over these difficulties and requirements first before diving into the setup. So, like in the training setup, it's important that we ensure the security and reliability best practices. Given that now PII data is actually entering our setup, we should be really sure that it's secure and up to date with the latest standards. And furthermore, medical experts are, testing, but also potentially now already making decisions with the outcomes of this tool. So we need to make sure that the expected outcomes of the model are actually shown and nothing is different than expected. Then, as said before, we need to manage GPU resources. So we rely on the hospital client's their specific setup and therefore either their on-premise system or their private cloud. Their budgets are often not super high, and to make this work, we have been doing a lot of work in optimizing scaling from zero. But yeah, this mainly led to many discussions so far, and how can we really optimally make sure that models are available, but GPUs are only running when they're required to, basically make sure we don't spend too much. And then finally, we want to make sure that we allow for sort of smooth transitioning to the production/clinical side. For this, we onboarded a self-service system in which a data scientist or engineer can basically add their model to the config of the application, and by pushing this config to the production side, actually enable their model. This allows for an easy transition, and this also means that the engineer doesn't have to fully understand the serving stack. We have a very flexible model backend to make this work, and we also set up an internal model storage so that they basically only have to add their model to the model storage and can push it to production. Now, let's first have a look at the infrastructure around our Serve app. So we host our app in AKS, where we deploy KubeRay, and we have access to both CPU and GPU node pools. Each worker, we then deploy Ray Serve with a head node that runs on CPU and basically is a router to route the call to a model to the right model in the right worker. Each worker has a specific Docker image that is basically forming the set of dependencies that specific model needs, and has access to GPUs when required. Furthermore, the access to data and models is again managed using managed identities to make sure that the worker can reach the model and can also reach data that is potentially required to serve the request. Now, let's see how that actually works in the Ray Serve application. So, as said, we have Kaiko inside, which behind it are our foundation models. Now, to actually call a foundation model, we first get a call to our head, which then routes the call to the right model. every model type you can think of as a different backend. So you could have transformers, or you could have vLLM, or you could have something customized. So each different model type has custom dependency set, a custom way of model loading, and their own inference logic. However, for each model type, you may have several models. You, for example, could have different language models of different sizes. And to make sure that the right model is running in the right situation with the right number of workers, we do auto-scaling and resource management on the model level. Furthermore, as said, we use our internal storage to simply download the model to the right worker without any overhead from any of the engineers. So let's take a quick look at what that means in terms of onboarding a new model. So we see models as an asset in Dexter, which actually means that we see a model as a similar thing as a data set. So once a model is trained, an engineer makes it an asset in our Dexter setup, and this makes it accessible in the model storage. Now, the next step is for the engineer to figure out whether the right worker type is available so that they can actually get the model type in our setup. This is found in the application, and it's basically a simple config which states that, well, there is a certain name for the model, and they can find back what that model type represents in terms of dependencies. And then finally, they add the model to the model config of the application, which basically just adds a simple model name, which version to use of that model, and what deployment type does this model actually use. That's enough for an engineer to add their model to our serve stack. So once that's running and the clinical assistant has access to the model, we can go to the clinic and sit with the medical experts to validate how the model does and whether it does as expected for them. So we do validation on multiple levels, and we leverage different approaches in this. So first of all, we do clinical validation, where we primarily focus on understanding is the model doing what the clinician wants it to do? So does it assist on the right things? This also involved validating the features in our app, but it's a really interesting way of actually getting an insight in how does the model perform, and if it makes a mistake, is it a very severe mistake, or is it actually something the clinician doesn't care about at all? Because then the other side of our validation is more focused on the general evaluation of the models. Here we leverage LLMs to actually scale our evaluation. But here it's sometimes very difficult to see how severe the errors made are for the clinical output. And what we so basically do with these two modes of validation is we take the insights from the clinical validation and the data from the actual LLM evaluation and feed this back into the training loop to further improve our models. So this concludes our model development cycle. Now let's dive a bit into the challenges we faced. Some of the challenges we've solved with Ray, some which we solved around it, and some that we're still facing. So let's first dive into the two main challenges that we solved using Ray. So first of all, that's the scaling from zero. I've mentioned it before, but in our clinical setup, the budgets are limited, so we need to make sure that GPUs are not running all the time and they're really available when they need to be available. So for this, we use the autoscaler config, and actually in our setup right now, most models are scaled down to zero most of the time, and they're up when the clinician needs them. One thing we still struggle with is startup time. We'll come back to that. Next to this, we wanted to make sure that our whole cycle is easily accessible for all the engineers, so that both for training and for serving, they can use the different tools without a lot of resistance. For this, we, for example, have a dev setup where each engineer can test out different things in their own clusters, but we also have K-Ray so that they can easily access the production clusters. Furthermore, we have an easy onboarding setup for our serving setup so that anyone can easily add a new model. Then some challenges we solved working around Ray, and interestingly, these sort of came back the last days also in other talks. So the first thing we needed to solve was actually authentication and RBAC support. In general, Ray clusters are accessible to anyone, and we needed to put the Ray endpoints behind protected ingresses. We used the Ray job submit hook for this, and well, that's eventually solved by Ray, but it took us quite a while to figure this out, and actually finding it in the Ray docs was quite a struggle. Next to this, we introduced K-Ray for easier interaction of our developers with the production setup. This adds runtime environment resolving, user management, and traceability. And finally, we added Ray to our logging stack, and for this, we leverage FluentBit. So as you probably know, Ray writes logs to a bunch of files. And yeah, you need to make sure that these logs actually end up in your stack. So we added a sidecar that basically subscribes to the different files and forwards it to the stack. One thing we still struggle with sometimes with Ray is that there is a lot of logging, but it happens in a lot of different places. And while the team that works a lot with Ray has a good understanding of what to find where, the engineers that just want to do their daily job, or the data scientist that wants to deploy a model, has quite an issue in finding back the right logs at the right time to quickly debug. Then I want to shortly go over 2 open challenges that we still face that might be interesting. You might have an interesting answer for us, but I wanted to share. So the initial challenge that we actually faced for the past year is one that's not completely related to Ray, but it's more related to CubeRay. We deal with very large models and large data sets which require access to additional disk space, but they need to be close to the GPUs. However, to provision a local disk, CubeRay needs to know on which node a worker is going to run. And the same holds to basically format a disk. The CubeRay needs to know which disk is going to be used. This leads to a bit of a chicken-egg problem where you either know the disk or you know the node, but you never know exactly, you cannot say basically they're together. We've been trying to solve this first with people from Azure, as it seems to be more of an AKS problem, but also trying to talk with the Ray team, but so far there has not been a really proper solution found. We currently solve it by basically provisioning a node and then on startup time running a script to make sure, okay, that we actually provision the right disk and assign it to that worker. But this is requires admin access to the worker, which is something you, well, likely don't want. And then, well, as mentioned before, one thing we still face is startup time when scaling from 0. We run, for most clients, we run in Azure AKS. So we first need to provision a node, which sometimes takes up to 6 minutes. Then we need to pull a Docker image to that node to actually make sure that the right Docker image is found to run the process. And then we still need to load the model into the GPU. So worst case scenario, there is a lot of downtime here. And yeah, this is something we will be working on to solve over the next months, because this is one of our, well, main challenges. So to conclude, at Kaiko, we build multimodal clinical assistant using our oncological foundation model. We leverage Ray, both in our training and serving setup. And, well, Ray helped us to overcome many of the challenges, but we still face several. So, yeah, thank you, and let's continue the conversation. Yeah, I like to get Dong on the stage as well. He is the one who worked more on train, so we can both answer.
Hey, great talk. You mentioned that you do most of your training on AKS. Is that because of HIPAA restrictions, or? So I'm curious if you chose AKS because of HIPAA restrictions, or you plan to use other cloud providers as well?
You can.
To repeat the question, so you're asking why we chose AKS, right?
Correct, yeah.
So it's mostly our necessity. So most of our clients use AKS, so we chose that as well, our necessity. But we do have plan to support whatever cloud provider that our client will have.
Yeah.
Because as Mark already showed, a lot of this on-premise requirement exists in hospital in Europe.
Yeah, and one thing we also, for specific now larger trainings, we also are onboarding a new cluster that's external, so not one of the big clouds, but yeah, that's also one of the solutions we took to fix this.
Thank you.
Great presentation. Can you speak a little bit about the model architecture? Like, are you guys using something off the shelf and customizing? Are you guys using DSpeed or Megatron to train? Like, just a little bit more information around that.
Yeah, I can talk a bit about that. So, on the one hand, for example, for the example you saw with the vision language model, we leveraged the Lava architecture, and there the vision encoder is our own foundation model, which is actually a public model. I don't have a link to it there, but if you, we published that model, I think, a year ago. And then the text encoder is I'm not 100% because I have not been involved with the training, but it is a medical language model mainly trained on PubMed resources.
And then for those two models, the text and vision, are you training foundationally, or you only have the?
Yeah, so the foundation model is completely trained on internal private whole slide images, and the text I think it is a language model fine-tuned on PubMed and then fine-tuned on internal, more Dutch language as well, because many of the reports are in Dutch. So that's, yeah.
Can you share how large your compute fleet is for training the foundation?
Sorry,
model?
can you?
How big your compute fleet is for training the foundational model?
So maybe you can.
Yeah. So the question is how big is our basic compute resources, right? So we recently acquired 64 GPUs from a node of H100. Yeah.
Any other question? Otherwise, yeah. Thank you.